Yes.
I really have to apologize for not being able to be there. This is actually the last week of teachings, and my popularity wouldn't have increased towards 70 students if I had been away this week. So I apologize for that. I would have loved being there and say hello to all good friends. And please also don't be intimidated by the 61 slides here. I'm not going to cover 61 slides. There is a lot of material as a backup. So, and I will skip some of the slides here actually. And I wanted to give you a kind of motivation and context for this type of calculations, which also align pretty well with Bryce's talk, the previous talk. So Bryce is actually a collaborator on this project here. And I wanted to say something about physics-informed neural networks and show you some results as well. That's basically the kind of thing. And the methods which you see here, and one of the reasons why we've opted for physics-informed neural networks is that you can actually add the initial conditions in the optimization problem. And this makes it appropriate for time evolution problems. And obviously, if you're dealing with quantum control, this is a topic which is very hot nowadays. So this semiconductor quantum dots is actually a hobby horse of mine. It's been around for me for something like 30 years after a famous paper by Hjorth-Jensen loss in 97 something. And these are artificial atoms. They allow for precise tunability as a function of particle number, a confinement of a harmonic oscillator or trapping potentials. You can tune interaction strengths, etc. It's at the intersection nowadays of condensed matter. There is actually platforms for making, or candidates for making quantum computing platforms, quantum dots in nano devices, but also the kind of system which I'm going to show you, which is actually very interesting and which has been studied experimentally by physicists at Michigan State. There's a lot of rich many-body physics. Even for few particles, you have a transition from a Fermi system to crystallization of Wigner molecule formation. There's a lot of interesting other stuff like spin ordering, non-trivial excitation spectra, and so on. So typical parameters would be the interaction strength or the Coulomb interaction, which is a typical interaction, the number of particles and the trap frequency. And in all many-body methods, we face the exploding dimensionalities. When I say we, it's obviously because there are lots of people involved, and you recognize many of the names here. And especially in this project is Jane, who was a former Michigan State student, Bryce, who you just heard, Alessandro Lovato, and also people like Stefano Gandolfi, with Arnau Rios and Giuseppe Caleo. And there is a recent paper, although this talk is actually not about nuclear physics, but many of the methods can actually be applied to nuclear physics problems if we are able to deal with, let's say, the time evolution properly of a system. Just a quick one. So we know that many of the traditional methods, they struggle when we increase the dimensionality of the systems. Exact diagonalization, which is one of the things we applied in the beginning, is restricted to very small n's. In Monte Carlo calculations, we have the Fermion sign problem, and the neural quantum states, which Bryce talked about, is actually a way to circumvent that, because you're still dealing with a variational problem where you have the wave function squared. DFT often leads to in strongly correlated regimes. So this quantum dot system is a kind of counterintuitive system. When the trapping potential gets weaker, then the electrons are on average more apart from each other. But what kicks in then is the long Coulomb interaction. And then many-body correlations become actually more important than the single particle properties of the system. So it's actually a system which offers a lot of interesting many-body physics, and you can actually control it in the lab easily. And mean field perturbation fails when the correlations are large, and basically all the methods struggle when you explore high-dimensional parameter spaces. And the approach which you've heard of earlier was the neural quantum states, which Bryce presented, but I'm going to focus a little bit on physics-informed neural networks. And we did this calculation for kind of model systems, but we also, because one of my other hobby horses is actually to study theoretically and experimentally what we would call many-body entanglement in systems which not only are interesting for quantum computing, So there is a long digression I wanted to give you so you can see the kind of axis I'm moving along. There is a set of criteria which DiVincenzo proposed back in quantum computing, and you have to have a system with well-characterized qubits. The ability to initialize the state of the system is actually a very important topic, which many of you in the audience here have dealt with. You have the need for long relevant quantum coherence times, which are typically long gate. You want to have a set of quantum gates you can realize, and you want to have a qubit-specific measurement capability. So these are some of the criteria which fully apply to many of the candidate platforms, whether these are neutral atoms, ion traps, semiconductor quantum dots, all the quantum systems I mentioned. So this is actually a system which has been studied by many people, and it's electrons trapped on layers of superfluid helium. And Johannes Polanen, who many of you recognize, is actually one of the main driving forces here. And this picture is actually, as you can see, it's taken during COVID. And we started this by chance, by just meeting. We just met at outside Sparty in a physics building during a coffee break during lectures. And then Johannes said that we have just bought these dilution fridges, and we are now able to cool down electrons down to very few millikelvins. Now, it took them something like 5 years before they were actually able to trap a single electron in harmonic oscillator lookalikes and even do the spectroscopy. And this is the experimental technique is actually pretty well detailed in this paper here. This other guy is Nias Beisingulov. He is now the scientific leader of a company which has been established by Johannes and which is called AeroQ, and it's based in Chicago. And the basic idea which they have is to use these electrons which are trapped on layer of superfluid helium as candidate systems for qubits. And the thing you can do then, if you can then isolate 2 electrons in these traps, you can then have well-defined low-lying states, which you then can identify as computational basis states, qubit 0 and qubit 1. And what we have been doing is, for this type of system, is to run theory simulations where we link this with reinforcement learning so that we can optimize the experimental parameters and find states or initial states which give a maximum entanglement, which then can be used in making quantum gates. So the typical device which we have been studying was a device where we were able to have this kind of anharmonicities in the harmonic oscillator trapping, which is simply a micro device where the 2 electrons are trapped in a double well potentials, which are created by electrodes. So that means that in this specific case, we had 7 parameters, which we tuned to maximize the entanglement of the system. And the electron's energy is typically in a double well electrostatic potential, and you have a screened Coulomb interaction. So that's roughly the many-body system. And one of the reasons why I wanted to have this long digression is that we as nuclear physicists, we have a long tradition to work closely with experimentalists. And this is one of the physical systems where we believe we have a theoretical model which is not that far from physical reality. So we've been actually, there are some papers, recent papers, where we actually studied the Coulomb-driven entanglement. And we used the setup to actually make or design, theoretically, 2 qubit gates. And one of the things which we're actually looking into now is to use this system as a system for quantum sensors, because entanglement is one of these properties which is expected to enhance the experimental sensitivity. There's actually, I should say, there are huge projects across the world, for instance, in high energy physics, to actually test out quantum-based sensors with a hope to be able to measure feeble, let's say, signals from, let's say, dark matter candidates, etc. There's a big project now at CERN, which unites something like 150 scientists across the world on devising quantum sensors using different platforms. So what we did in that specific case was actually to, for this paper, these papers, we actually have 2 electrons, and this is something you can, with the standard many-body physics, FCI, you can actually diagonalize the problem. So you have a tool, you have a method which everybody is familiar with, and you can actually study these systems, and then you can use, I'm going to skip some of the slides here, what we actually had. I hope you can forgive me if I do that. So the thing we did then was to use reinforcement learning. And I think this is also something for, if we think of nuclear physics, agent-based AI, reinforcement learning, etc., are machine learning or AI methods which are very powerful when it comes to link both theory and experiment. So what we did in this double well setup, where we have a model-aware reinforcement learning, we believe actually that the theoretical model we have can then be used to in an implementation of reinforcement learning, and the agent controls the electrode voltages, and the reward is the total entanglement, the entropy of the 2 electron state. So reinforcement learning then finds the voltage correlation that maximizes quantum correlations. Actually, this, as I promised you, a long digression, this could have been a talk by itself. So I'm sorry for that, but I just wanted to mention it because it shows how we can use many of these machine learning techniques where we can use both an experimental environment and a theoretical setup to find optimal experimental parameters. In our case, the experimental setup is tuned so that we can maximize the entropy and the entanglement entropy. And the entanglement is one of these features which one thinks enhances many of the properties of quantum computers, and many of the algorithms are actually based on utilizing entanglement. So one of the core challenges is actually that many of these quantum devices are delicate. Small imperfections lead to decoherence and loss of information. And reinforcement learning has actually proven particularly powerful because you have agents which interact with a simulated experimental quantum system. You learn protocols that optimize the desired objective. And the state preparation and high fidelity gate implementation is one of the typical applications which you would study in these kind of setups. So one of the problems with the experiment, which the experimentalists face, is simply that they know how to do the electronics, but they have so many parameters that they may not know which are the interesting parameters. So that's why we combine these theoretical models with machine learning, like reinforcement learning. I also wanted to say something about many of these techniques. This is my kind of vision of kind of future discovery. So we are very much used to have theory, simulations, and results. But what we are seeing now is a new paradigm which is emerging with an integrated knowledge where you handle complexity and uncertainty through fusion of theory, data, and computations. And the traditional high-performance computing approach is now being broken up in many different aspects, which include quantum computing with high-performance computing facilities. You have AI for science, model generation, optimization, etc., etc. So the combination of these basic technologies is something which I think will be crucial for future discoveries. I'm just going to skip that one. So let me come back to where Bryce left with the neural quantum ansatz, and pins. So the basic idea when you do a variational Monte Carlo with a neural ansatz, you typically minimize the Hamiltonian expectation value via Monte Carlo sampling. You can deal with large number of particles, typically study ground states. With pins, you can enforce specific symmetries, and you can include continuous space, complex geometries, time dependence, initial conditions, and boundary conditions. So one of the key advantages here is actually the fact that you have a wave function which is learned as a continuous function of particle coordinates. And you would typically also bake in anti-symmetry. You would have normalization and conservation laws, which can be imposed as explicit constraint or penalty terms. So typically the way you would set it up is that you have a cost/loss function where the n here is your residual, typically squared. That means the difference between the left-hand side and the right-hand side of your differential equation. In the calculations which we had here, we simply had only this part, and then we had the boundary conditions because we looked essentially just at the time-independent problem, and we're just targeting the ground state of the system. We could have added initial conditions, etc., etc. So it's the machinery is very flexible, and with automatic differentiation, you can actually evaluate the first derivatives and second derivatives almost exactly to floating point precision. The thing which is nice, you can generalize in machine learning. You means consistency with physical laws, not merely accuracy in unseen data. So you have an algorithmic stability of gradient-based optimization, implicit bias towards smooth, low complexity solutions, and then you have also an architectural inductive biases which encode domain knowledge. So there are lots of, I'm not going to read everything which you have on the slides here. And by the way, you have actually access to the slides because Dean has probably uploaded them to the website of the STREAMLINE meeting. So you can actually look at many of the things which are here afterwards if you're interested. So one problem, if you design the pins as it stands, is whether it respects the variational principle. So that's one of the big issues. And you can actually choose two different strategies in the optimization. You can have a variational and you can have a residual based one. And they have slightly different fundamental properties. And the first one is obviously variational, but the other one is not necessarily. So what Bryce has been doing is actually to use the variational principle, where psi now is a wave function, which is defined by a neural network, where theta are the parameters of the neural network. And then you simply optimize this problem here. This equality holds only for the exact ground state, as everybody knows. Now, the any admissible trial state gives an upper bound. Now, the problem when you look at the other strategy where you optimize the residual, that enforces the Schrödinger equation directly, but there is no guarantee that the variational principle is preserved. So one of the checks which we did when we run this calculation was actually to make sure that we actually run two calculations, one with a variational based one, and then the other one where we had the residual minimization, and we checked that we got the same results, or approximately the same results. So if you take the residual based physics-informed neural network, there's no guarantee that this relation is respected. So you can actually get results which are below true ground state. You can have a convergence to incorrect states, and the residual is small, but the solution error is large. So in general, this kind of approach here, which we want to use when we look at the time-dependent Schrödinger equation, does not, in general, preserve the variational principle. So you have to add additional checks, and in order to preserve the variational principle or observe the variational principle. So I'm going to skip some of the slides, so you can. I'm not going to present everything. So one of the things we did was actually to optimize a function where we have the standard function, which is optimized in a variational approach. We had additional boundary conditions, and also you can impose specific symmetries with a penalty parameters in front of them. So one of the things one should avoid often is to make the residual the dominant loss term if variational upper bounds are required. So we typically use the energy quotients as the primary objective. But we have run both types of calculations, and when we typically run the residual pin, the solution which we had is a solution which we then would plug into a variational calculation as well. So this is roughly a summary of the way we would enforce the different methods. So we have the variational bound, which is enforced by the standard variational pin, and then we have this standard variational approach, and then we have the PD, which is enforced explicitly in the residual physics-informed neural network. And normalization must be added then. And there is always a risk of solutions which are below the variational bound. So this is just some takeaways from the type of calculations which we have performed. So the kind of variational structure is something which we have to consider built into the loss function. Okay, so some other technicalities which I wanted to say a little bit about. I don't know how familiar you are with quantities like stochastic reconfiguration in Monte Carlo calculations. So when you do the optimization of the neural network, stochastic reconfiguration is actually a way to replace the standard quasi-Newton-based approach where you have an approximation to the Hessian matrix. And then you actually introduce something in the standard Monte Carlo machinery, something which is proportional to the classical Fisher information. This has actually some nice, interesting connections with quantum machine learning, where you actually have the equivalent of the classical Fisher information, which is called the quantum Fisher information, which essentially is the second derivative of the log of the wave function. And it mimics, in a way, the properties of the Hessian matrix, which you would have in the optimization part. Then there is also another trick which is used in these Monte Carlo calculations. And for the Monte Carlo practitioners, there's something which is called backflow, which I have explained in the next slide. So typically, when we look at the ansatz here, we often bake in the anti-symmetry. Bryce didn't talk about the Pfaffian approach, but that is also one way to bake in the anti-symmetry. We have baked it in terms of a Slater determinant, and where the coordinates here are actually updated by using backflow. And I just have a machine here which keeps beeping. Sorry for that. I just have to switch it off. Sorry. So if you were disturbed by this noise in the background, I hope it didn't spoil the fun here. So the four components here, you have a Slater determinant, which you can often tune with the Hartree-Fock basis. You have to introduce the adjuster factor, which often is given by a cusp term for the Coulomb part. And then there are some compact permutation invariant neural correlators. I will say a little bit back, you have the backflow, which is typically only inside the Slater determinant. The backflow is often a shift. The standard backflow is a pretty common approach, which is used in Monte Carlo calculations, and it actually updates the coordinates. And the coordinates, if you think of that one, I mean, what you do then is introduce something which is physically motivated. It has few parameters, but limited expressivity and no access to higher body structure. So, but the kind of analytic pairwise form is the one which is often used. There are other types of backflow, and I won't have the time to go through that, but I put in a lot of slides in the appendix. And if you want to look at it, I mean, you can take a look at this other type of backflow here. But since my time is running out a little bit, I just wanted to show you some results first. And this is a calculation of quantum dots, where we also have some reference calculations from diffusion Monte Carlo, which is a kind of standard benchmark in many body physics. For 2 electrons, this is actually one of the few many body cases where you have, with realistic interactions, where you have exact analytical calculations. So you can actually solve the 2-body problem in a harmonic oscillator trap with a Coulomb interaction analytically, because you can separate the relative motion part and the central mass part, and then solve just the relative motion part with the Coulomb interaction. And the energy is actually, the exact one is free for a frequency of 1 in atomic units. And our best result here is basically on par with the exact analytical result. And you see that when you move to trapping frequencies, so I should also say that these trapping frequencies are still frequencies where the mean field dominates. So in a certain sense, I mean, I'm not hiding things, but I'm actually showing results where a mean field or Hartree-Fock calculation would still do a pretty good job. And but what you see here is that, and this correlates pretty well with what Bryce also showed, is that we get results which sometimes are actually below the diffusion Monte Carlo. So these are diffusion Monte Carlo calculations which were done 16 years ago by Francesco Pederiva, whom many of you know. So clearly these are calculations which could be redone actually. Now the network here with this backflow is actually pretty shallow. It has only 2 hidden layers and 100 nodes in each layer. So it's actually a calculation which is not too time consuming. And this is actually a little bit more interesting. This is actually something which we have not explored properly because quantum dots, when you go to these very small frequencies, the electrons, when the potential well gets very wide, what happens is that the electrons on average are apart from each other, and you would actually expect that the correlations would be negligible. But what happens in this case is that the kinetic energy, if you think of the harmonic oscillator trap, the kinetic energy and the harmonic oscillator energy actually drops to 0. The electrons come to rest almost, and they get localized. This is a typical sign of what we normally call a Wigner-Seitz crystallization. The thing which we haven't studied is actually the character of the wave function here. So these results are pretty new, actually. The calculations were finished in the beginning of May. So there are lots of things we want to analyze, in particular the results at very low frequencies. So we have not analyzed the structure of the wave function. But however, in the cases where we can compare with diffusion Monte Carlo calculations, the results are actually pretty close. Now then we did another thing, and I'm going to skip this one, but I actually wanted to say, this is the last thing I wanted to say something about, so I don't abuse too much on time. So what we did, and because one of the things I'm really interested in is to study many-body entanglement. So what we have done is to run calculations where we have 2, 3, 4, and 6 harmonic oscillator wells. So what Johannes Polanen want to do is actually to have many qubits. And that means that they want to trap many electrons. So what we can provide them is a theoretical study of many-body entanglement. But in order to be sure we have that what we are doing makes sense, we have to have many-body methods which we can rely upon. So we, in a way, it's like when we do the nuclear many-body problem, we must be able to say that we do trust the calculations which we have done. So what we did here was actually to run this pin case for a case with 2, 3, 4, 6 electrons, where we have trapped, we've made the barrier between the different harmonic oscillator wells so high that we can localize 1 electron in each well. And then in each of these wells, we have kept only 10 single particle states. And what we have here is the calculation with a truncated CI calculation, because for every harmonic oscillator well, you have an infinity of single particle states, but we just kept the 10 lowest one. And also when we went to 6 particles, we actually had a very truncated CI calculation where we kept only 500 states. So for that specific case with 10 single particle states, we would actually have had 10 to the 6 configuration. So the CI calculation is actually not a benchmark, but we tested the pins calculation where we use the CI calculation as an input to the pins calculation in order to see whether we could get something meaningful. And we found a spread and a max error which was acceptable. Actually, these studies are very, very preliminary. And the reason why we've been moving into the systems is obviously that we want to look at the time evolution of this system. And that's why pins are interesting candidate systems for many-body methods, because we can actually, by baking in initial conditions and the time dependence, we can actually study, after having prepared the initial state of the system, we can then study its time evolution. So that's a kind of long-term goal here. I should also say that these kind of systems are not that different from the way we think of nuclei. So a lot of this formalism could actually be applied to time-dependent problem in nuclear physics, a particular time-dependent problem like fusion, especially if you have few particles here. Actually, this is a digression. Sorry, guys. So one of the things which we have been doing as well, which I haven't shown here, is to develop what in many-body physics has a long acronym. It's called multi-configuration time-dependent Hartree-Fock. And we've been comparing that with time-dependent copper cluster theory with singles and doubles. So the kind of idea is then when we have a time-dependent pins, we actually want to study the different many-body methods and see if, obviously, if we get more or less the same results. That's a kind of one of the next steps which we want to look at. So as a summary, I think the accuracy actually with respect to DMC is pretty good. The deviations which we found overall, and these are standard diffusion Monte Carlo, it's not auxiliary field Monte Carlo with a fixed node. It's actually pretty close to these results. And I think it's a very promising method. I think we have a broad applicability. You can easily go to other systems than just 2D or 3D trap systems. And we want to study the real-time dynamics and excited states. And the final goal is actually when you have a reliable many-body method is to try to match this with agent AI or reinforcement learning so you can link that with an experimental setup and fine-tune the parameters with a combination of theory and experiment. What we've been using is what's called model-aware reinforcement learning. And for those of you familiar with Bayesian statistics, you will recognize many of the key basic elements there. So the advantages is that the wave function is a continuous one of the coordinates. It can give an access to excited states. We haven't done that. You can look at complex geometries by the boundary conditions. You can look at time-dependent problems. And if you look at the advantages when you do the variational Monte Carlo with a standard neural network, is that this is almost now an established workhorse for large n-ground state calculations. And you saw from the calculations of Bryce that this is a very powerful method to attack larger nuclear systems. So basically, yeah, open questions, future directions. I already mentioned some of them. One of the topics which I'm very interested is actually the real-time dynamics. And that means to extend what we have with time dependence. So roughly this ends what I wanted to say. I think I just went 2 minutes over time. I hope you can forgive me for that.
Thank you, Morten, for this very, very comprehensive talk. So let us have questions then. Thomas.
Hey, Morten. Your comments about time dependent intrigued me. Do you have any results to show?
We have only results for multi-configuration time-dependent Hartree-Fock.
That is good enough.
So that's and we have a group of world-leading quantum chemists with the Trygve Helgak and company, and they have actually made quite some progress with the orbital time-dependent copper cluster. So right. What we wanted to do is actually to compare these pins with what we get from multi-configuration time-dependent Hartree-Fock, which we have only applied to 2 electrons now, simply because the dimensionality explodes. So this is really, Thomas. I think if you come back to the fusion problem, this is a hot topic which one should explore properly.
Okay, Dick.
Hi, Morten.
Hey, Dick. Hey.
Is there any gain from considering the minimizing the energy variance instead of or in combination with minimizing the energy?
No, that's actually a very good. It's a very good question because a comment because I mean with the variance, you know exactly what you should get if you have the exact wave function. The only problem then is that you get actually I think 7, 8 additional integrals which you have to evaluate. So when you calculate the gradient of the energy, you have the log of the wave function integral multiplied with the local energy, and then you have the log of the wave function and its derivative with the local energy. So you have 3 integrals to evaluate when you calculate the gradient, and that is already one of the I'd say one of the bottlenecks to have a precise evaluation of that, because you evaluate these integrals by Monte Carlo integration.
Right. Okay.
So, but you know, I mean, what's the name of the Monte Carlo guy, Umriger? I mean, he devised this method, and many people actually, I think Bryce and Alessandro Lovato also tried out the variance optimization.
Yeah, I think these days people do some combination of other stuff. The variance doesn't work very well.
Yeah.
Okay.
Now we haven't done that actually, but it's something we would like to actually include. So it took us some time to get stochastic reconfiguration to work properly, but and that actually gave a much better optimization problem, because previously we just did the standard approximation where you had ways to update the learning rates with optimizers like Adams or root mean square propagation.
Okay, thank you.
Yeah.
Hi, I have a question about I think a problem that a lot of people run into when they use these pins is that they get stuck in this very challenging optimization problem where their optimizer is satisfying the PDE loss, but doing really bad on the boundary condition, or vice versa.
Yeah.
I wonder if you observed that here. And then I don't know if you mentioned it, but you gave us a comparison of Monte Carlo with your pin plus backflow models and the other one. But how much does the pin actually help? Like could you have dropped the pin loss and still gotten a very good answer, or maybe even a lower ground state energy, but maybe have I don't know, broken some symmetry that you wanted along the way? Or
so one of the things which we normally do routinely, because if you start with a residual, you may actually get astray and not be able to optimize properly. So what we often do is that we run a kind of preliminary variational Monte Carlo calculation with a neural quantum state, and that serves as a starting point for the pins calculation. And that is something which speeds up the calculations normally. So, but there are several, I think I have a long list of several bottlenecks which you can run into. So pins can often be tricky to optimize, as you say. But we've been guiding the optimization by a simpler neural quantum state. So you run a cheaper calculation, and then you have the parameters to initialize your neural network with. And that has often given us a better convergence.
Thank you.
Okay. So let us thank Morten again. The last speaker for today is Daniel Lee. And Daniel's topic is generative AI and Schrödinger bridges.
Yeah, I need to, I think, share the sharing. Yeah. Good. All right. I can put it here too. The point is there. Okay, thanks. All right, thanks, VTech. I'm gonna change gears a little bit because I know very little about nuclear physics. So what I wanted to do today was give you a little bit more of a tutorial style talk about some of the latest things that are happening on the machine learning AI side in generative AI. And I wanted to try to relate that to some of the physics principles that I think we all know, so that can maybe give you some inspiration and ideas for some future work. So this is what I wanted to do today, to kind of give you this kind of overview. So, okay, so what I wanted to, first of all, I wanted to try to discuss several topics. I wanted to see how many people have heard of the Rickatim here. Some of you, okay. Have people heard about Schrödinger bridges before?
Just at lunch.
Just okay, all right. But Hamilton-Jacobi equations, right? People should know.
Sure.
Okay, so I'll try to cover aspects of all these things in my talk today. So what I wanted to do is just to try to introduce you to what we mean by kind of distributions and flows between distributions, and then how we think about it as a topic in terms of optimal control and dynamic programming, and then how we add noise to these systems, stochastic systems, and then there's again a connection to optimal transport. And then that gets us to Schrodinger bridges, the problem that Schrodinger introduced a long time ago. So that's what I wanted to try to cover. Just some caveats here. This is actually a very active machine learning research topic these days. I can only cover basic things here, and that's because I don't know about some of the advanced stuff that's going on, because that's really recent. And I'm also going to give you, hopefully, a physicist point of view. So, I hope no one here is really a mathematician or, computer science theorist, because they wouldn't like this approach to trying to understand this material. So hopefully that resonates with most of you here. Okay, so what's the motivation? I think you've heard a lot about the success of generative AI. One of the kind of key types of examples of this is reverse diffusion processes in order to generate images. And the basic idea is to be able to take a system, right? You take an image and you can think about a forward diffusion process by adding Gaussian noise to it. And then the idea is to learn kind of a neural network that can learn how to take Gaussian noise and basically learn the kind of flow to give you back to an image, right? That's kind of one standard example of a generative AI system. And so kind of the paradigm of generative AI is you have some data set, some set of images, some set of whatever in terms of data. You then have to figure out how to model this density distribution. And then you are able to then sample from this distribution to give you kind of a novel, image from this distribution. So that's kind of the overall kind of approach. Now, how do we do this? Well, first thing you have to understand that these density distributions are in high dimensional spaces, right? So what we have to do is try to figure out some way of modeling this really high dimensional probability density function. And, what's critical is really kind of how do you build this? So kind of in the old days, in machine learning, we would build some sort of Gaussian models, mixture of Gaussians, parametric models to try to do these density distributions. And they didn't really work that well on these really extremely weird density distributions. So what's happened now is we've shifted from that kind of parametric approach to trying to actually learn how to kind of map more standard distributions to these higher dimensional distributions. And that's what I'm going to tell you about today. Yeah. Okay, so here's examples. Now you might have one density data set, but you can also have multiple data sets, right? And this is kind of multimodal data. So you can imagine, having a distribution of, say, cat images here. You could have a distribution of dog images. You could have a distribution of images of digits, handwritten digits. You can have a distribution of the structures of proteins, right? Audio images. And so kind of what we like to do in AI is to figure out some general way of comparing and aligning all these different distributions to each other. Okay, so that's kind of the overall motivation of what we want to try to do in this kind of, kind of a generalized generative modeling. Okay, so here's the kind of idea. You give me two data distributions. So let's just say the set of cat images, right, in some pixel space, and some set of dog images in some pixel space. Let's call, one image, one data distribution row 0, and the other distribution row 1. Okay. So here you're just given samples, right? So you're given samples of cats, given samples of dogs. You're not given any other information. You don't know, what correspondence there is. The question is, how do I compare just this density row 0 to this density row 1? What's a good way of trying to do this problem? Okay. And so, this will give rise to something called what we would call unpaired data translation, right? So giving some, some density, arbitrary density row 0, some arbitrary density row 1. If you could try to figure out how to map correspondences between kind of points in one distribution to another one, we can then do many things, right? We could basically sample from one distribution and then generate the kind of corresponding sample in the other distribution. We could go backwards. We could then match up things that go together, right? And to be able to then do in some sort of supervised kind of way of translating things from one space to another space. Okay, so that's the idea. Okay, so kind of the standard approach that's existed in machine learning to do this is something called optimal transport theory. Okay. Have people heard of optimal transport before? Okay. The idea here is the motivation actually comes from Napoleon times. This is called the earth mover problem. All right. So the idea is that you have some, mound of dirt, and you want to construct, right, some fortification on some fort. So you want to make another mound. Why? So you have some distribution row 0, and you want to make it into some other distribution row 1. You have some sort of transportation cost, right, which tells you how much it costs for me to move a piece of dirt from this location to that location. And the idea then is you want to come up with some sort of transportation plan that tells me, take a shovel of dirt here, move it over here, and then, by doing this kind of transportation, you'll then optimize the most efficient way to kind of move a distribution from here to here. Okay, and that's kind of the motivation of the problem. And this is called the earth mover kind of distance then. All right, so the way we can actually solve this problem was done by Monge and Kantarovich. And the idea is interesting, right? Instead of thinking about one distribution and the second distribution, think about the joint distribution, row X and Y. And what we want to do is somehow optimize over all joint distributions, which have the property that the marginals are constrained. So in one direction, the marginal is row 0. In the other direction, right, the marginal is row 1. Okay? And this then, we want to optimize the joint distribution with these constraints such that the integral over this joint distribution with the transportation cost is minimized. Okay, that's the way we formulate this optimization problem. And the idea here is then this joint distribution tells us the transportation plan, right? It tells us for a point, piece of dirt at X location, I can look at the conditional distribution along this column, and that tells us where this guy should move in Y. Right, so this joint distribution really is then the kind of plan that tells us how to move pieces from here to the pieces in Y. Okay, so by lifting this problem from kind of two separate distributions into a joint dimensional distribution space, this makes the problem then very well tractable. Right, so this has kind of been known, and this is an old problem. But what I want to do today here is to explain kind of how this is used and then how to generalize this to more dynamical settings. Okay, but so here is an example why this is a kind of useful principle. So imagine being able to take one distribution, say you take your images on your photo gallery, right? So pictures that you've taken, and now you have another distribution of images, right? Like say images from Matisse's drawings. And now if I can actually do this transportation plan, where I can map points in my photo gallery to points that look like a distribution of Matisse, this is how you can actually then generate cool images, right? If you can do this properly, you can take your photos from your image and figure out how to kind of map them into the space of some particular style or content. All right, and that's the idea. And this is why these techniques are so powerful for application purposes. It allows you to do this kind of style transfer. Okay, is that clear, the idea? Okay. All right. But what I want to talk to you today is not the standard optimal transport theory, but the idea is that instead of just telling you that this point corresponds to a particular point over here from row 0 to row 1, we want to also be able to tell you how this point should move dynamically from this kind of initial row 0 to this final row 1, and how then another point in row 0 would then move to row 1. Okay? So we want to understand not only how points are corresponding, but we want to also know how actual samples will move or interpolate between these distributions. So this is what we call dynamic transport, right? We want to understand how the path that they actually should take. All right. Okay. So in order to understand this kind of dynamics, we have to understand a flow, right? The way we describe the dynamics is as some sort of velocity flow field. It tells us, at a point in this position will start to move along this velocity direction. And the particle motion is then described by some differential equation that just tells us by integrating the flow, this is actually the path that the particle takes. So the dynamical motions of particles are described by velocity flows and differential equation. Right? So we're going to build this into the theory so that we can understand how to do this. Okay, so this is kind of how reverse diffusion models work, right? Is you give me some distribution, you take a standard normal distribution, rho one, right? And what you do is you figure out the flow that, diffusion processes take to go from points here to kind of a standard normal distribution, Gaussian distribution. And then you reverse the flow. Basically, what you get is a score function that you have to learn. And that reverse flow then tells you how to take samples from a standard Gaussian distribution and go back to your original distribution. That's kind of the basis of reverse diffusion models. So this is why the concept of flow is very important for trying to build these models. Okay. So, but I want to introduce, learning these flows in the context of control. Okay. So, the idea that you're going to steer kind of particles basically from one distribution to another distribution, I can think about that as kind of controlling a system, right? So instead of steering particles, think about steering cars through some sort of landscape. You can imagine that controlling flow from one distribution to another is basically trying to understand through this flow field how we're steering these individual particles to their goal positions. Okay. So what I want to now do is introduce some basic principles from control theory that allow us to understand how to do this optimization better. Okay. Clear on terms of that? Okay. All right. So let's just start with a very simple system. And this is a discrete time system. So imagine that we describe the dynamics in the following way, right? You give me some, particle at some state position, xt. We then add, some basically velocity to it. And then we get some, we're controlling this flow. We get to some new state at some time t equal to 2. We then add a flow there. We get to some time xt equal to 3. And so I have now a discrete time dynamical system. And kind of these are characterized by state vectors that change in time, in discrete time. And then we have these controls, these control actions that tell us kind of how to kind of move the particle in time, right? This is the most simple, basic dynamical system that we can run. All right. Now, when we do optimal control, we have this dynamical system that tells us how the particles evolve. We have these states, we have these control actions. And now the issue is we want to figure out how to set the controls in time such that we get to some sort of final states that have kind of minimal cost. Okay, so the way we do this is we write down some cost function that tells us kind of what's the cost of moving these particles so we can have some sort of terminal cost at the last time instant. What's the, it wants to be in certain positions, as well as some sort of cost of moving the particles at each time. Okay, so the idea in optimal control theory is write down some objective function that depends upon the whole trajectory of these particles, right? And now we want to figure out how to set the sequence of controls in time so that we minimize this particular cost function, okay? So that's why we have this optimal control problem, all right? Okay. Now, the naive algorithm, right? This is what students would first do, is I have some objective function. I have to optimize over these sequence of control actions, right? I'm just minimizing this. So, the naive way of doing this is you basically evaluate over all possible sequence of costs, right? So you do some for loop of U0, for loop of U1, you do this huge nested for loop, you sum up over all these costs and you try to figure out which, sequence is basically the best one, right? That's kind of the naive algorithm that, basic students will first do, okay? Time complexity here is exponential in time, okay? So this is intractable. This is not the way you want to solve this. So how do you solve these problems? Well, the way you solve this is there's an interesting principle. It's called the Bellman principle of optimality. And it tells you something about shortest path problems, right? So anytime you have a sequence or a path, essentially, if you tell me that this path is optimal, then any subpath also has to be optimal. Because if it's not, then you could always do better by cutting that out and do a little bit better on a subpath, right? So if you tell, if you say that the optimal path to go from New York to Los Angeles goes through St. Louis, then that path from St. Louis to Los Angeles should also be optimal, and the path from New York to St. Louis should also be optimal, right? I mean, that's the principle, okay? And this allows you to then basically simplify these path optimal sequence problems, okay? And this is the principle of dynamic programming, right? So the way you do dynamic programming is if you actually want to, search over all possible paths, you just have to do it kind of recursively, right? So, you say, if I want to get to Los Angeles, right, in this node, I can look at nearby cities to it and try to figure out, how much time would it take to get to Los Angeles from Phoenix or from, Seattle or something on the West Coast. Then you figure out, from there, which one's the best path to get to Los Angeles. Then you look to see kind of recursively how to get to either Seattle or Phoenix or, Denver from, the Midwest. And then you then recursively then push back. And so this is Dijkstra's algorithm, right? Well-known Dijkstra algorithm to solve this problem. And the way you do this is you compute this cost to go function that tells you kind of what's the total remaining cost that you need to do, and you kind of continually minimize this over subpaths as you do this process. Okay, that's how you solve these problems. Okay, so that's the idea. You define an optimal cost to go. So you take your cost function, and you say that there's this value function, optimal cost to go, that tells you that from a particular position, starting at that time, what is the minimum of that subpath going to the end of time? Okay, that's the cost to go, right? So starting from a particular time, then if you actually minimize over the subpath to the final time, big T, then if you minimize that, that's the optimal cost to go. And then you can kind of recursively work your way back on this optimal cost to go function, right? So you can start with then at the final time, and then you can recursively kind of try to solve this, all right? And that's the Bellman equation. Is you write down a recursive relationship that tells you how the optimal cost to go function depends upon, and you do this recursively, it tells you how the optimal cost to go function at time t is related to the optimal cost to go function at time t plus 1, and then you solve this to basically do your dynamic programming. All right, this is much, much more efficient than the exponential naive algorithm. All right. Okay. People heard about dynamic programming before and things like that? Okay, all right, so that's the idea. Okay, so the way you would then solve this optimal control is you initialize this optimal cost to go function, you then work backwards, right, to calculate this optimal cost to go, and then once you have the cost to go function, you can then go backwards forwards again, which will then tell you the optimal path to follow by following the optimal cost to go, right? That's how you solve these problems. Okay, so let me give you a concrete example, all right? So let's take a linear system example, right? So I have a dynamical system, basically xt plus 1 depends upon some linear matrix times xt. And then I have some control vector ut that also influences by some control matrix b. The most simple, basic, dynamical system. And let's say that the cost function is quadratic. So I'm trying to optimize some quadratic costs on the final state. And then I have some cost and some intermediate states, as well as costs on my control actions that I'm taking. Okay, so this in engineering is known as a linear quadratic regulator problem, right? It's a linear dynamical system, quadratic function, and I'm trying to minimize this, so I'm trying to regulate this down. Okay, so how do you solve this problem? Well, the cost to go function in this case is also quadratic. So it's a quadratic with some coupling matrix PT. You then do Bellman equation. So you can initialize, what is the cost to go function at the final time, big T. You then write down Bellman equation, and then you write down then how the cost to go matrix is related at time T to the cost to go matrix at time T plus 1, right? That's Bellman equation, okay? And so you can solve recursively all these quadratic cost to goes. And then this is how you solve the linear control quadratic regular problem. This is called the Riccati equation, the algebraic Riccati equation. Okay. All right. Okay, clear on the discrete time. Now I'm going to go to continuous time. So suppose now instead of discrete time linear dynamical system, let's go to this continuous time. So now instead of a system here, we have a deterministic ODE that tells us kind of how things flow in time. We now change our cost function. We can write down the cost function as an integral over all time. And then the control problem is to find now a function of time, right? The optimal control is now a function of time that minimizes this cost, okay? So when we go from discrete time to continuous time, we go from, a discrete update to this differential equation, and our cost function is now an integral rather than a sum. All right. Okay, so when you calculate the value function, the cost to go function, This is called the value function. It's the same thing we learn in reinforcement learning. Then if you show what is the equation, the kind of the recursive equation for the value function, it turns to be basically another partial differential equation. Okay, this is called the Hamilton-Jacobi equation, right? It tells us then how the optimal cost to go function is related, right? And so the way you solve this, you have some terminal boundary condition, and then you can then work backwards on the PDE to give you the optimal cost to go, right? So this is, how you solve it using Hamilton-Jacobi, right? You have this ODE, dynamical system, you initialize the cost to go function, you run a backwards partial differential equation to get the cost to go at all time t, and then you can then use this to calculate, the optimal path in time. Okay, that's how you solve these problems. Right? So here's the example. If you do a linear quadratic system, again, you have some linear ODE as a dynamics. You have some quadratic cost function. You then have a value function, which is also quadratic in time. It's a quadratic function. But this matrix, the quadratic coupling matrix for the value function, depends upon the time t. And then you have this kind of differential equation that is a matrix differential equation that tells you how the quadratic cost to go function depends on time. And then you got to solve this. Okay, so that's how you solve a continuous time LQR problem. This is called the continuous algebraic Riccati equation. Okay. Final step is you got to add some noise. Okay, so instead of now dynamics where it's deterministic, imagine now you have some Brownian motion. Okay, so now the dynamics is now determined by a stochastic differential equation, not an ordinary differential equation. And you have this Wiener process, so you have some Brownian noise added to it. The cost now is not just an integral, it's an expectation over all possible random variables. So you have to take the expected cost, that's your objective function. So how do you handle this? All right. Well, the way you solve these problems is that because it's a stochastic differential equation, you no longer have a deterministic state in time. All right. So what we do in machine learning is we define a distribution over all possible states. Okay, so at each time t, instead of being at a certain position, I'll have kind of a possible set of positions. This is something called what we call the belief state, okay, in machine learning. So we have to now track, instead of tracking a particular state, we have to track a distribution as it changes in time. And this is known as the Fokker-Planck equation, okay? So the Fokker-Planck equation just tells us that, basically how this belief state, how the distribution over possible states in a stochastic differential equation would change over time. And that tells us exactly how, what this distribution satisfies. Okay, so this distribution in time satisfies the Fokker-Planck equation. The way you figure this out is this equation, a continuity equation. You just calculate the flux in, the flux out. You can then basically then describe the time evolution of this belief state. Right, that's where the Fokker-Planck comes in. Okay, so so I won't go into the details, but what you can then show is these reverse diffusion models. If you look at the Fokker-Planck equation, you can basically reverse time, the diffusion term that occurs in a stochastic differential equation. You can reverse it by basically, generating a flow field, which is the gradient of the log of that row. So that's something called the score function in machine learning, and that's how we do reverse diffusion, is basically look at the Fokker-Planck equation and figure out how to make it time reversed. And then basically we do that. Okay, so, but I won't get into the details. Okay, but this is where then the Hamilton-Jacobi-Bellman equation comes in. If you solve this value function, you now have to take, expectation, you have to then do the stochastic differential equations. If you solve this, then you can actually write down the Hamilton-Jacobi-Bellman equation, which has, a Laplacian term in it, which is then how you solve the Hamilton-Jacobi equation for stochastic differential equation. All right, so that's the effective noise. The effective noise, the difference between noisy stochastic systems and deterministic systems is you have to consider in the Fokker-Planck equation, you have a Laplacian term on the distribution, and then on the Hamilton-Jacobi-Bellman equation, you also have this Laplacian term that you got to solve going backwards, and that's the way you solve these things. Okay. All right, so that's, now I won't go into the demo. So that's, a quick summary of optimal control theory in the context of these kind of dynamical systems. right? So now let's go back to this optimal transport problem, our original problem, okay? We want to figure out how to convert basically a distribution rho 0 to a new distribution rho 1, right? I told you that the static problem was just to basically write down a joint distribution with some cost function and minimize this objective function over a joint distribution, okay? Now, if you do this with the Euclidean distance, this is something called the Wasserstein 2 optimal, a distance between two distributions, but that's kind of used for in the machine learning community. All right. Now, when you solve these problems, they actually like to add a little bit of regularization to it. Okay, so instead of just optimizing this objective function, what they actually end up doing a lot of times is they add a little bit of entropic regularization. Okay, what they do is they add a little bit of penalty here term on the entropy of this joint distribution. And what that does is it gives you better properties on the solution. The graphics is not so good, but what happens here is that with different entropy levels, you smooth out basically this solution so that, without entropy, you can have kind of very discontinuous solutions. Like as soon as you change the distribution, rho 0, rho 1 a little bit, you jump kind of where the particle should go. So by entropy regulations, you smooth out these optimal solutions. And so that's how typically you use this in practice, okay? But what I want to tell you a little bit here is how to convert this problem with dynamics. Okay, this is static, right? I just told you X and Y, how to map X to Y. What we can then do is actually make a dynamic formulation of this problem where we say that, there's some particle at time t0, and then the particle at time t equal to 1. But now I want to think about this particle moving along some flow going from 0 to 1. And so the trick that you do is actually just take this Euclidean distance and you rewrite this distance, just like we do in physics all the time, as some integral over some delta function, okay? And the delta function here is just some straight line path going from X to Y. And then we can write this, distance as basically a minimum over all possible paths, but you integrate the velocity squared term. And so if you minimize the velocity squared term, you'll get a straight line path, which then gives you this term, okay? So if you then put that back into the problem here, we can rewrite this as some integral like this. We then, do all this. So we can now derive a dynamic formulation because now we have explicitly a time going from 0 to 1 into our optimization problem. And this is then, turns into a dynamic density distribution. So the idea is the following. I can think about a joint distribution at time t equal to 0 is the marginal distribution projected along this axis. At time t equal to 1, it's the marginal distribution projected on this axis. But at intermediate times, it's like rotating the marginal distribution along some angle so that it has a dynamic distribution that changes in time. That's the way you can kind of see what's happening to this joint distribution. Okay? So, I don't want to spend too much time on the details, but this leads to what's known as the Benamou-Brenier formulation of dynamic optimal transport. And the idea is the following. The optimization problem to solve an optimal transport problem is we want to minimize from time 0 to time 1 a flow field, a velocity field here, V. We're going to minimize that, and we're going to minimize the kinetic energy of this flow field, okay, over our distribution at time t, over our belief state. Okay, so this is the velocity, the average velocity kinetic energy of the distribution at each time, and we just integrate over time from time 0 to 1. Okay, but the constraints are the following. The constraints are that the distribution has to be matching rho 0 at initial time, and it has to be rho 1 at the final time, and the distribution, basically satisfies the equation of continuity. So the distribution changes according to the flow V. So this is the equation of continuity. So if you solve this optimization problem, this is equivalent to the Mondrian-Kontorovich static formulation. It tells you exactly how X goes to Y, but now you have a dynamical system that tells you how exactly each particle is flowing, right? And that's the optimization problem that we could solve, right? So here's the picture, right? You have an initial distribution rho 0. You have some final desired distribution rho 1. You have to design a flow field V in time such that particles flow according to this, simple ODE. All right. And we want to minimize then basically just the kinetic energy of the flow field over time. Okay. If you do this optimization, you get the optimal transport plan that tells you exactly how each point goes to the kind of points over here. Okay. So if you want to solve this, you can do this as an optimal control problem. You write down that Benamou-Bronier. You can write a Lagrangian to include all your equation of continuity. And you can actually show then that the optimal flow field is really the gradient of the value function. That's the solution to the Hamilton-Jacobi-Bellman equation. The gradient of that is actually the flows that you need to use for this optimal control problem. Right? That's just, the relationship. Okay, so now finally I want to get to the Schrodinger problem. Okay, this is what Erwin Schrodinger talked about in 1930s. Okay, his idea was, imagine you have a hot gas system. Okay, so you have a hot gas system with some distribution, like say it's in a box at time t equal to 0. Okay, you let it go, and the gases move around, the particles in the gas move around, and you observe it's in some cloud, it's in some new configuration at time t equal to 1. It's in some cloud. Okay, so you see the kind of initial distribution. You see another distribution rho 1 at time t equal to 1. And you know that gas is diffuse, but also it does something else. And so it turned into this new distribution rho 1. So there must have been some forces at play that sculpted it so they went to some new distribution rho 1. So his question was how to discover the forces on hot gas particles that are consistent with this kind of observed distribution at 2 different times. That was his problem. Okay, so now you see the connection here, right? This is something called the Schrodinger bridge. We have some stochastic differential equation, right? This tells us how the gas particles are moving in time. We have some velocity flow field, but we don't know this velocity flow field. So but this is the dynamics. And what we want to try to do is solve for this unknown velocity flow field that minimizes basically the kinetic energy of this velocity flow field under the constraints that now we have the Fokker-Planck equation because we have diffusion. So the constraint here is the Fokker-Planck equation, and the constraint is at time t equal to 0, it's distribution rho 0, and at time t equal to 1, it's distribution rho 1. Okay? So this was the Schrodinger bridge problem. You have to solve a kind of a 2-sided boundary condition that has kind of the Fokker-Planck equation as the internal constraint. And we want to minimize the kind of energy of this flow field that causes us to see the distribution at time 0 and the distribution at time 1. That was his problem. Okay? And so this is the picture, right? You see this gas particles at time 0. You see the gas particles at time t equal to 1. They undergo, some velocity flow along with some diffusion process that makes them so that they appear in this new configuration. And now you got to figure out what is the kind of the best optimal set of flows that would do this. Okay. Okay. It turns out that this Schrodinger bridge problem, we optimize over these flows, with the Fokker-Planck equation, is exactly equivalent to solving the optimal transport problem, but with entropy regularization. The entropy term in the regularization for the optimal transport problem basically corresponds to the diffusion process in the Schrodinger bridge problem. Okay, so you can solve this problem in 2 ways: one, the static formulation, or with a dynamic flow field like this. Okay, and I just give you a comment. So the way we computationally solve these problems is we have these it's kind of difficult, right? You have 2 boundary conditions, kind of initial time, final time. So the way you do this is you have to kind of iteratively project your solution so that it satisfies that initial boundary condition and the final boundary condition. So they have some, basically what you do is you have some solution and it doesn't satisfy the initial thing, so you have to project it onto this distribution, and then you run it through your dynamics, and then it doesn't satisfy the final one, so you project that, and then you run backwards, and so you go forwards and backwards until you converge to both distributions. So that's the way they solve these problems. Okay, so these are called iterative proportional fitting, Sinkhorn types of algorithm, and so you have these kind of alternating half bridge problems that they're solving. All right. Okay, so let me just complete by, why is this useful? So what you can then do is do things like this, right? You give us a set of cat images, domestic cat images. You give us a set of wild animal images. I learn, this mapping, no correspondences. I just learn cat images and wild animals. And now you can figure out, how cats flow to wild animals and how wild animals flow back to cats. And so you can then make this kind of correspondence. It's hard to see the resolution is not so good, but you can basically do this kind of translation from one domain to the other domain. Okay. Here's another more practical example where they take CT images of brains as well as MRI images. Okay. You don't need to have patients that have simultaneously had a CT and an MRI. You just take images of people that just took the CT, other people that took the MRI. You just have kind of two distributions. You learn now through these processes how to map them together, and you also know the flow. Okay, so what you can now do is basically take someone with a CT image, flow it according to what it should do, and it's now going to interpolate basically from CT to its corresponding MRI, and you can flow backwards to get then the reverse. Okay, so that's when you learn this flow, you can do all these kinds of things as applications. Okay, so that's all I wanted to cover today. So hopefully you have an idea of this is kind of different from your normal supervised and regression problems or RL types of problems. This is really an unpaired data translation problem. You can think about it in different ways. There's this optimal flow control, right? So we need to transport one distribution to another distribution. And then you see that there's this, this old problem, the Schrödinger bridge, which is connected to this entropy regularized optimal transport problem. And so you can see now, there's a very active area in trying to scale these up to, all sorts of kinds of distributions with, large data sets. Okay, so thank you very much.
Great. It's so interesting. I wonder, is the entropy regularization that prohibits chaos or positive level exponent where basically we just go from noise to something?
Yeah, so if
how does one prevent chaos with these things?
Yeah, so if you don't have the entropy regularization, what happens is if you change, one of the distributions a little bit, you completely change the solution. So this gives you kind of smoother solutions as kind of the sensitivity to the actual inputs, right? So that's what the entropy regularization. It's kind of like viscosity regularized kind of solutions in differential equations, right? So that is assumed.
In principle, it's impossible to take a diffuser, what you had on your first slide. It's literally impossible to just give you noise and then make a cat out of it, right?
Well, they do.
They do,
Yeah.
But I don't know, if I would randomize a cat, I could not.
Yeah, so I mean, the idea is that you take these cat images, right? So the forward process is that you think about diffusion process. So by adding Gaussian noise to a cat image, it eventually turns into a Gaussian noise image. So if you learn how to reverse that flow, then I can start with a Gaussian noise image and turn it into a cat. That's
how you mentioned. Maybe you mentioned earlier.
Yeah, that is how it's done.
But I mean, come on now.
Yeah.
You cannot fold a function and then unfold it and obtain the original one. This is usually not possible.
But you get the distribution back. It doesn't say that you get points back. It just says that you get the distribution
Right.
back.
An element from the distribution,
Yes.
not the same that you started.
Yeah.
Yes.
So you get a sample from the distribution, and the distribution is correct.
Yeah.
That's what the guarantee.
Yes, Pablo?
Super cool, anyway. It's always a pleasure to hear. My question was, I guess, for actually the physicists in the room. I was trying to think if we could apply any of the things that you were saying to kind of make correction elements from theory to experiment. But then I thought probably these things work best when you're talking about high dimensional objects. It would be silly, I guess, if I try to apply these numbers to numbers. Like if I have a theoretical calculation of a nuclear property and I have an experiment and it's very few numbers, maybe it will not work. But the question is this something we could use to apply when you have a calculation that is less expensive and it gives you wave functions that are not as accurate, and you have the other one that is more expensive and gives you more arbitrary wave function. I'm thinking something like if I have my DFT models and I get my single particle wave functions that are nice and I can do that across the entire chart, but then I have some ab initio stuff that is more expensive. Could we learn such mapping using these things?
Yeah, so I wouldn't use it if you knew correspondences. Like for instance, if you kind of said that I knew this theoretical value and this simulated value correspond to each, then you have paired data. You should use that information because it's a lot, there's a lot of information. Here, these methods are like you don't have any kind of pairing, right? So imagine that, I don't know, maybe you have experiments and you don't really know what they correspond to from theory, and you have, you know, maybe multiple theories or something that generate things. So in that case, you might have an unpaired situation where you could try to do something like that.
Is somebody online too?
Morten.
Oh, how do I?
Yeah, Morten, go ahead and speak.
Can you hear me?
Yeah, I can hear you.
Thanks, Daniel, for a very nice talk. So just a curiosity, because you listed the stochastic ODE for updating the x's. Is that something which you would do with something like a Langevin updating? Is when you propagate through the different steps in the diffusion process?
Yeah, exactly. So the stochastic differential equation is just a Langevin dynamics.
Yeah,
It's
right,
exactly
right.
the same. Yep. So
So
that describes that.
Yeah. So how much would that differ? So if you think of the standard, let's say a variational diffusion model, where you have an explicit recipe for propagating the points through the different steps when you denoise the equation and when you put in noise. So at the end you have a blurred equation which you then image, which you then reconstruct. So how much does it differ from, let's say, the traditional approach in a diffusion model?
No, so you can map it to the reverse. So the forward process typically in diffusion model is easy, right? Just Langevin adding noise.
Exactly.
The hard part is to go backwards, and there you have to learn kind of a flow field that actually like undoes the diffusion process that you did in the forward direction, and that's the hard part. And so that's what these systems are learning, is the optimal flow field in some sense that gives you the best mapping.
So what's your feeling with the compared with, let's say, a variational diffusion model when it comes to performance with this approach?
I mean, so the kind of what people are doing reverse diffusion now is trying to make it more efficient, and and using the neural networks to approximate the optimal flow in some sense. And so it might not give you the optimal solution, like, but it's good enough to give you a nice picture, like when you generate, but it might not actually match the distributions properly, which people are still thinking theoretically, and how to prove your methods would guarantee the proper distribution. So that's kind of where some of the differences are between, in practice, what people do with these reverse diffusion models, and, here theoretically about optimal transport.
Thanks, Daniel.
Very nice to hear. A lot of equations are a little hard for me to follow, but anyhow, so my naive understanding is that the information was encoded in a flow, say the equation, right? Some the V equation. So imagine we can from some random image, and then you can do that flow equation to get some meaningful image. So my question is that the control, the information, all of the information comes into that equation, but can we have do we have some control of that? For example, what I was thinking is very last week of slides you showed the image between X-ray and MRI, right? So do we introduce more or new information from X-ray to MRI, or it's the same information but with a different kind of form?
Well, okay, so there's several things here. So first, I should point out, here on the Schrodinger bridge problem, right? The idea here is that you're learning the flow field that basically takes you from row 0 to row 1. Now there are a number of flow fields that will do this, like go from row 0 to row 1. Now the optimization is such that you actually minimize the energy of the flow field. Okay, that's what gives you the optimal transport. Okay, so that's why we learn this with this structure, is that it gives you some sort of optimal flow. Okay, and then this allows, in some sense, it's kind of the most efficient path for the particles to take. And so when you do this, interpolation between things. You know, you don't have any data in their interpolation, right? You are basically, this flow is telling you the best way to interpolate the kind of the data examples, and you generate new data examples that you never saw. So like, you know, when you take your photos and turn that into the distribution of Matisse, it turns into an image that Matisse never drew, right? You only had a few samples from this Matisse distribution, but it turns it into something that looks like Matisse, but it, you know, is more better related to what you actually gave as input. So that's why these things are useful.
Just out of curiosity, considering these flows, do you ever have to worry about the non-ergodic systems?
I think the assumption on all these kind of proofs and stuff is ergodic and things like that. And it's not infinite time, right? It's kind of finite time. So it's not like we're, you know, going to infinity sampling.
Okay. So the main thing I was wondering about is like there exist distributions that you can't connect. For example, like there doesn't exist a flow between.
Yeah, I mean, maybe you probably could construct some very, you know, measure zero kind of distribution that do this, right? So.
Yeah, so this might be a little bit of a naive question, but so if you're minimizing for, like, with respect to the flow field, you can kind of quantify the performance of that flow field. But once you're done and you have that way to go from one distribution to another, how do you evaluate the quality of that result? Because I feel like when we usually apply machine learning methods in physics, we like to have like a very quantifiable understanding of like the performance of the result.
Yeah. So, I mean, the typical way you quantify after you learn, you know, these reverse diffusion model, you try to calculate, you know, you generate now new samples and you try to calculate some sort of log likelihood to see whether it gives you good likelihood under, you know, that new distribution. So that's the way they quantify the performance of these systems typically. That's something.
Very good.
Yeah, so again, that maybe I'm maybe more used to thinking about the paired data, but everything here is very much like an RG flow, right? A unitary flow from an initial to a final theory, or an initial wave function to a final wave function, or an ab initio wave function to a mean field wave function, or preserving phase space volume. I mean, the Hamilton-Jacobi is about finding the optimal canonical transformation of your phase space volume in the classical mechanics literature. So is there anything useful that we people who are familiar with this kind of stuff could be bringing to I guess I mean, we normally don't deal with the stochastic noise on top.
Yeah, so there's stochastic noise, but some of the older flow models, something called normalized flows, you know, was basically under the constraint that the determinant was one, the unity, right? So it basically preserved phase, right? That's okay. These new ones don't do that, right? So for instance, you can map, you know, a low dimensional manifold district, because that's the idea. Like these, say, set of CAD images are actually on a low dimensional space, and you map it into a high dimensional Gaussian. So it cannot satisfy the normalizing flow constraint. So this is what allows you to actually do these kinds of things, right?
Can you say a little bit more about the regularization and how you're deciding what the epsilon t is?
Yeah, so when they do the entropy regularization, it's kind of like a hyperparameter typically people use, and then they're basically doing something to try to see whether, you know, by changing this, essentially basically you're going to be able to make this energy smaller, right, as with more regularization. And so they titrate this somehow using as a hyperparameter, I mean, experimentally.
Okay, so it's just more empirical.
I mean, my impression is that's how most people treat it.
Okay, that was my question.
Yeah.
Okay.
So you presented all this in the continuous X. Of course, you did discrete time. But of course, computers don't have continuous images with pixels, and all of this is discrete. And so equality is some sort of, maybe this is all in like a vector space, and these are inner products for considering for equalities or similarities. It's a long way to lead up to. It seems like this is completely compatible with mixed data types. So the row 0 is images, row 1 is a token string or
something, it doesn't matter, if you can define similarity via an inner product or whatever else. And Heiko, this is maybe getting to where the reverse of Heiko's question of where can we contribute, this is maybe where this is useful in a physical context where we're comparing things that aren't the same objects. Is this done in literature anywhere? Of course, there's text to images, but you've been talking about image to image.
Yeah, okay, so the way you have people handle text to image or whatever, this is all kind of is flow in a particular vector space. So the way they do it in practice then is they do some text embedding into that vector space, they do image embedding into that vector space, and then they learn the flow that maps in that kind of embedding space. So they use a joint embedding space typically, and then figure out kind of how things move to each other. That's the way in practice people do it. Now there's newer also work on these kinds of stochastic processes on graphs, and that allows you to do some sort of like directly on tokens as nodes in a graph, and then you do some diffusion process and flow by basically moving in a graph. So that's kind of these discrete kinds of types of models, right? And that, so these people trying to use that to try to replace LLMs essentially for these kind of discrete language generation. And that's a huge active area of research right now.
So, did actually Schrödinger solve the bridges problem?
He wrote down a lot of the equations I showed you, is that, the optimality conditions that you would need and things like that. And, the half bridge problem. And he related actually to Schrödinger equation in terms of a kind of a forward flow and a backwards flow. And like you can factorize the wave function. I think I'm not, somewhere must be in a Schrödinger equation, you can actually write the wave function as a product of two wave functions, and that one goes forward in time, one goes backwards in time. And then this is kind of like actually he wrote down some optimality conditions of that, which is exactly solving this type of problem.
So Eric, I was surprised you never made this analogy to fission and instantaneous. There are so many similarities.
Yeah. Okay. Great.
Okay.
All right. Thanks very much.
Thank you.
Okay, so remember we have a dinner at 6 o'clock at the Pizza House. So a lot of you probably will want to walk there, but if you want to have a ride, let's say people who are local or people who have cars, let's meet here 10 minutes before 6, and so that we can give you a ride there. Okay.